Okay, now that we've tackled our exponential equations, we're going to jump to logarithmic equations. And the process will be similar. Okay, so remember how we solved exponential. We kind of had two types. We said, well, if I can write it with the same base, then it's going to be easy. And we're going to do that with logs. We're going to see that as well. And if I can't, then I have to use that property of the relationship between logs and exponents in order to solve. Okay, so similar, not the same, but similar. So let's take a look. That first type is if I can have this, if I have logs on both sides of the equation, just like if I had exponentials, I can just drop them. So I can use a log property here, right? And here's my property. If the log base a of x equals log base a of y, then x equals y. That is, if I have the log with the same base on both sides, I can just drop them. And I almost have that here, the natural log of x minus 5, but if I apply first a property, so leave the left-hand side alone, and then what property can I use here? The sum of two logs is the log of a product. Okay, so this is my easy case for logs, which we won't spend a lot of time on. I got the log on both sides, and I can just drop them, and I get a nice, easy linear equation, which I know how to solve. Negative 5 equals 3x. Divide both sides by 3. Oh, important concept to talk about here, because this actually is not a solution. So I'm glad we started with this one. X equals negative 5/3 is a solution to this equation. But what I haven't considered is the domain concept for this, right? So I just went ahead, just did all my math and solved. But what I have to consider is what could x be, or what could x not be? I can't plug a negative value into here because I can't take the log of a negative. Remember our log function, I can only take the log of positive numbers. Okay, so I can't plug a negative in. So if I do the math, so we're making an assumption here. When we apply this property, when I drop the logs, we're assuming that all the x values are okay, or we're assuming there's certain rules that are followed. So typically in math, we kind of ignore those assumptions, and then at the end, we check them. And that's what I'm doing here, and x cannot be 5/3, because if I plug in, or sorry, negative 5/3. So I plug it in here, then I'm taking the log of a negative number. So there's actually no solution. The solution I get is called extraneous. So in this case, there's no solution. So we'll see that come up from time to time. We see it in our first example. Always check, do your math, check your work. If you have a negative answer, or just plug it back in. You don't have to plug it in to see if you're right. Just plug it in to make sure you're not taking the natural log or any log of a negative. Okay, that's the quote-unquote easy case where I drop the logs. Now this is the one we're usually going to do. If y equals a to the x, that should say, typo, then x equals log base a of y. This is my definition of logarithm. Okay. So, how do I jump back and forth between the two? I got to go this way. This will be my method. If I have a log, I'm going to use what I know about exponentials to solve this. So I rewrite it as an exponential. What's the base? 2. Base, base. What's the exponent? It's what the log is equal to is the exponent. In this case, 3. So 2 to the third equals the input of the log is the output for exponential, right? That's my inverse property. So let that sink in. That's the key step for these. You can just undo the logarithm or write it in exponential form. Sometimes I do this. 2 to the third equals what you're taking the log of. And now the log's gone. So 2 to the third is 8. Once I get there, it's easy. I usually have either a linear or a quadratic to solve. And I'm good. Make sure you check it. Plug that back in. 7 plus 1 is positive, so that one's okay. That should work out. And you can do the whole check if you want. You could say, is the log base 2 of 7 plus 1, is that equal to 3? Well, that's the log base 2 of 8, and that's definitely equal to 3, right? 2 to the third is 8. All right, let's do another one. Okay, so this, I had two log expressions, but I got a sum in between. So we'll often use our log properties like we did in that first one. And this is the sum of two logs is the log of a product. All right, so this is my input to the log, and now I do the same thing. 2 to the third is equal to that. So 2 to the third is equal to the input of the log is the output to exponential, And let's see, should we multiply them together? Well, let's just do one extra step. Solve this thing. Well, that's 8. If I FOIL that, that should be x squared minus 1x squared minus 1x plus 1x minus 1. The x terms go away. I can subtract 8. How do you want to solve this? Well, we can solve by factoring, or we can solve by taking square roots. Let's say I left the 9 on the other side, or I could have added 8. I'm sorry, I could have added 1. X squared equals 9. I could have done it that way. Either way, just remember there's two solutions. It's not just x equals 3, it's x equals positive 3 and x equals negative 3. Even if I did that by taking square roots, I would have got x squared equals 9. And take the square root of both sides. Don't forget your plus or minus trick. Plus or minus 3. Okay. Check your answers. Now remember, if I plug in a 3 here, positive, that's good. That's 2, that's positive, that's good. But this one's not going to work, right? If I plug a negative 3 here and here, I end up taking the log of a negative. So that's no good. So I leave him out. That's extraneous. So I have one solution for this one. X equals 3. Let's see. First, isolate log just like we did with exponents. So that's the natural log of 3a minus 5 equals 1/2. 2 over 4 is a half. Now do the thing, right? There's a little e here, base e. E to this power equals that. E to the 1/2 equals 3a minus 5. That's a little funny looking. That's a square root of e. I can leave it either way. Add 5 to both sides. I'm going to divide by 3. And I get this weird looking answer. A equals that thing. Now that's hard to check, but I could check it. Plug it in at least. I should check to see if I'm getting a positive. And I think that should be positive. Let's do the check. A equals this thing. So is this true? That's 4 times the natural log of 3 times this solution, 5 plus e to the 1/2 over 3 minus 5. Is that equal to 2? That's the original equation. So I put a little question mark here. Is that true? Those go away. Those go away. So is 4 times the natural log of e to the 1/2, is that equal to 2? Well, it should be by 4. That's a half. I can see the natural log of e to the 1/2 should be a half. So I'm pretty sure that's the correct answer. All right. You'll see we've already seen this application before. It was exponential growth. You'll notice this is just like my money problem. Initial amount e to the kt, where k was positive. And that's an increasing exponential function. But if it's negative, it's just decreasing. So let's see if we can adapt to this thing. Stable radioisotopes has initial mass of 100. That's 100. For 10 days, the mass decreases to 60 grams. K falls in exponential. Okay, so this one's a little different. This one we actually have to find the constant rate, okay, or the decay rate rather. So let's see if we can do that. So we have the following. It goes from 10 days. So at 0 days, let's organize ourselves. We got 100 grams. That's the mass. So at 0 days, that's the initial amount when we start. And then after 10 days, it's gone down to 60. Okay? And what I need to know is K. So let's see if we can figure this out based on what we have. All right, so what I would do is, I'm just trying to figure this out. I write my function. I say, all right, I got 100 to start with. It's decreasing, right? If they just gave me the rate, which I do with the money problems, if it was your money's decreasing at 5% a year, you could plug it in and you'd be done. This one's a little more challenging. They're going to say, okay, find the rate itself. So this is what I know of my function. I just don't know the rate, but I can use this other bit of information to find the rate, and then I'll have my function. So think about it. This is t and this is m. So if I plug in 60, I know this has to be true. That's going to be the initial no matter what. And then when the input's 10, the output's 60. You do this when you solve like linear, when you're trying to find like the y-intercept of a linear function. You take a point, you plug it in, the slope's fixed, and then you find it's very similar to that. Okay, so now instead of solving for t, which we do a lot with those money problems and exponential growth problems, we're solving for k. All right, but the math is the same. So I'm going to divide by 100. And then I have e to the negative. I usually write it as 10k equals, what is that, 6/10, 0.6. I'm going to take the natural log of both sides because we like that property that cancels out everything but the negative 10k. And this should work because the natural log of a number less than 1 is negative. Okay, so this will actually give me a positive value for k, which is ultimately negative overall because the model says it's negative. I hope that makes sense. This will spit out a positive number when I plug it into my calculator. 0.051 is what I'll round it to. So I plugged it in just like that, and positive 0.051. But when I solve for k, so the negative I've already counted for because I left it in when I solved. So that works for me. So my function then, which is the question, I get the initial amount, which was 100, e to the negative 0.051 t, which is in days. We found k. If we wanted to check that, then this other point should hit this point. That is, if I plug in 10, I should get an output of 60. Okay,